Okay. Yeah, hi. So, oh boy, I don't even know where to start now because that was essentially most of my talk. I guess this is why we should organize better with in this conference. But I mean, I'll cover some new things, but yeah, that was essentially my talk. So I spent most of Brandon's talk thinking of jokes to make, and I guess if sequencing of talks is some structure, it must be idempotent since the two Brandons aligned together must have just been one Brandon, but yeah. Yeah. So we're going to talk about monoids, but I'll be live coding it, so at least maybe that'll be just a little bit different. And so you've already got all the definitions, so I could just start typing without, I should probably just copy and paste maybe, because, all right, so I'm going to define a semigroup as this thing. I'm just going to go straight for the operation. I'm not going to even define that op method on the protocol. We're only going to communicate with semigroups via their operation. And so this, you just kind of stick it in, and now if you had a semigroup, you could start diamond operating the things together. And of course, most importantly, like Brandon said, it has to be associative. If it's not associative, then you're destroying so much good structure. And so we could start maybe making some of these things, kind of defining some semigroups. We could maybe extend integer to be a semigroup. And then we got to define the diamond operator on it. It's got to go from an int to an int. And we could just do the most obvious thing. This is associative. Now int is a semigroup. So now we can use it, like this. Thanks. Okay, there's quite a few semigroups that we can just construct from Swift's standard library and from their kind of base types. So I'll just paste them in. Array could be made into a semigroup by just concatenating. In some sense, it's not that array is a semigroup, it's rather an array of elements is a semigroup, because array is kind of like a type constructor, right? It takes a type, spits out a type. So it's not quite a monoid in of itself, but if you have an element, like an array of integers, the type of array of integers forms a semigroup by concatening. String, also you can concat. Bool, you could also make a semigroup by just doing and, like left-hand side and right-hand side. You can show that these are associative, and so now we have a whole bunch of semigroups, which means it's kind of interesting to sit here and be able to write, something like this, using just one operator to kind of encompass many different types of computation, like the most fundamental unit of just taking two things, combining it into one. So then so even though this is seemingly like Brandon said, maybe a little strange to do this because it doesn't look like we're getting much. Already though, we do have this idea of reducing or folding or concating. I'll just make a free function called concat, and it's going to be generic over some semigroup. And if you gave it an array of x's of type S, and you gave it some initial element, you could then completely omit any idea of accumulation, because a semigroup just naturally comes with an idea of accumulation, taking two things and combining it into one. And so from that, we could produce an array by just reducing the x's and then using our little operator. Yeah, sorry. So it folds the entire array of s's, or concats the entire array of s's. Yeah, sorry. Wait, no, sorry. There we go. Yeah, so now we can concat any array of semigroup values, like 1, 2, 3, give it an initial, and this is, of course, just a sum of integers. We could also concat a nested array of things, and with an initial of an empty array, and you get the thing out of it. All right, so here's an example of something how we were able to reduce how we're able to simplify the concept of reducing by getting rid of one part of it. We got rid of the idea of accumulation because semigroup naturally knows how to accumulate. So then, if we wanted to even further simplify, we would define a monoid. So I'm just going to paste it in. So now a monoid is going to be a protocol that inherits from semigroup, and it just comes with the idea of like a starting point, an identity. And so there's axioms to hold left and right. So like E combined with anything is the same thing as anything combined with E, which it just leaves that anything fixed. Now we can make all of our previous semigroups into monoids quite easily. I'll just paste it in. By picking like the natural identity for each of their semigroup structures. 0 for addition, empty array for array, empty string for string, and true for Boolean because we used and so true and anything is that anything. And so now that we have this distinguished element, we can make an even simpler concat, even a simpler way of combining lots of monoid values, which I'll still call concat, but now it's generic over a monoid. And now all it needs is an array of those monoid values, and it will return just one monoid value. Because now we have a natural place to start. We can just use the monoid's identity, and we have a natural way to accumulate the monoid operation. And so now we can start using this. Say we could take the 1, 2, 3 array, now do not provide any starting point, and we just kind of naturally get what we expect. Okay. Now let's construct more exotic monoids. So the type of all functions from a type to itself. So not A arrow B, but just A arrow A. The set of all those functions naturally has like a monoidal structure. In math, a morphism or a function from A to A is called an endomorphism because the source and the target are the same. So I'll just create a struct called endo, and it's generic over A, and it's just going to have a little function sitting inside it. And then we can very easily make this a monoid. So the identity, let's start with that. So the identity needs to be a function that when you compose it on the left or right, or wait, no, sorry, not the identity. Let's define the operation. So we need that little diamond operation. We'll have the left-hand side is endo, the right-hand side is endo, and it needs to produce an endo. So what is this operation going to be? Well, you can apply the left-hand side, and then you can apply the right-hand side. And because the function went from A to A, you don't have to worry about sources and targets matching up or anything like that. You get it all for free. So we can just return an endo that applies the left-hand side first, and then applies the right-hand side. And now we have a semigroup. Yeah. So now we have a semigroup. If I just, for a moment, change this to semigroup, the compiler should be okay. And so I'll add monoid to it, and then I'll implement the identity. So the identity element of this monoid is going to be what function can we compose on the left and compose on the right and not have changed anything? Yeah. So we'll just return the endomorphism that just doesn't do anything. It's just the identity function. Okay, so now I'm going to kick up some endomorphisms. We could have the increment morphism, endomorphism. So it's an endomorphism of ints in which we just add 1. I could do another one, which is maybe square. That's an endomorphism of ints that squares numbers. I could do the endomorphism of, say, mod 3, and that just takes the value mod 3. And then I could start doing fun things like concat an array of increment square mod 3. And I've gotten a endomorphism back. What does it do? Well, it increments a value, it squares it, and then it takes it mod 3. So I could invoke that on, say, 3. Let's see if, oh wait, am I getting a compile problem? Yeah, what am I missing? Ah, sorry. Yep, that would be testing if it's divisible by 3, which is not an endomorphism. Okay, so I took 3, I increment, got 4, I squared, I got 16, I took mod 3, that's 1, because 15 is divisible by 3, and then 1 more. Okay, all right, so I keep on applying this, kind of getting more and more benefits out of it. Now, the idea of like a data pipeline, I'm just taking an array of endomorphisms and concatenating them together and then feeding data through. So, all right, that's kind of looking good. There's another interesting monoid you can cook up from existing. Given an existing monoid, you can cook up what I'm going to call function M, which is going to be the set of all functions from A into a monoid. And this is an example of a far more general idea of like the set of functions from, say, A to B, any structure that B has, you can almost always induce that structure on the set of all functions into that like structured object. So in this case, I'm mapping into monoids, and the set of all those kinds of functions, I'm going to put a monoid structure on it. All right? So let's start with the operation. You'll have to have a left-hand side of function M, a right-hand side of function M, and it's going to return a function M. This kind of mostly writes itself, so I need to write a function M, all right, and it's going to be a closure that takes an A and produces an M. All right, with that A, I've got 2 things I can do. I can use the left-hand side to map it into the monoid, and I can use the right-hand side to map it into the monoid. Now I have 2 monoidal values. I might as well combine them. I need an identity. So it's got to be a function M. So how can I construct this thing? Well, since it has to be a function M, it has to be a function that maps from A into the monoid, so that when I point-wise map 2 other function M's and I combine them, I get like the identity inside. The only thing it could be is to use the identity on M, so it's just a constant function on A. You can verify the axioms. This thing now forms a monoid. We now have a way of constructing monoids out of monoids. Okay, cool. So like a small digression, maybe in some future world of Swift, we could have a struct function AB and not do this function M, just allow A and B to roam free, and then we would maybe someday be able to extend function to make it a monoid in the case that B is also a monoid. So this kind of like protocol conformance isn't allowed. Or maybe even in a further future of Swift, we could maybe even extend like just arrow as a concept and make it monoid where B is monoid. But that's not possible. It's not so bad. I mean, we're going to get around it, and we're going to get a lot of benefit out of it without going all the way. Okay, so some specializations of this function M are very useful. For example, the idea of a predicate is a function from any type into Boolean, and Boolean is a monoid. So the set of functions from any type into Boolean is also a monoid. So I'll just define predicate as function a predicate on A as a function M to bool. Oh. It does type check, yeah. All right. So let's cook up some predicates. I could do a is even predicate. What? Okay. All right. Is even, if I take it mod 2, it must be 0. I could also do is less than 10. Whoa. Okay. Yeah. What? Oh. Okay. I'm looking at a very small version of what's up there, so I can have like notes and this going on at the same time. Okay. So I could take this is even and now monoidally combine it with is less than 10. And now I have a new predicate which encompasses the idea of being even and less than 10. I could also use these ideas to like induce kind of predicates from known Swift types. I could cook up a is less than function that is generic over all comparables, and given a comparable, it will generate a predicate on C where you just do the obvious thing. All right, so now I could even just get rid of that is less than 10 and do an is less than like 10. Like now I get it a little bit more out of it. I could also make standard Swift types even understand the idea of predicates by extending array and making my own filtered by predicate, where it takes a predicate on the element and returns an array. And I'll just filter self on predicate.call. So it's really just only a small amount of stuff I'm doing in there. I just don't want to see the .call everywhere. That's all I'm really doing. Okay, so I could like cook up a large array of say like 100 values, and I could do filtered by is even and is less than 10. I could cook up an array of strings and do the idea of filtering by is less than f, right? And get that. Yeah, and you're getting like a lot of things out of this once you kind of get that baseline of composable pieces. Here's another monoid, and this one we're going to cook up from scratch, and it's going to be called the ordering monoid. It's going to be enum with 3 cases: LT, EQ, GT. That kind of encompasses the idea of being less than, greater than, or equal. It just has concepts, not dealing with actual values. All right, and we're going to make it a monoid by first defining its operator. I'm just gonna, I'm gonna copy and paste it, because the thing is, I think the best thing to do with this is to actually sit down and trace out how this thing kind of gets used. But essentially, combining an LT with anything on the right just gives you an LT. Combining a GT with anything on the right gives you a GT, and combining EQ with anything gives you that anything. And there's a natural identity, which is just the EQ. Now the compiler should be happy. Yeah. Yeah. All right. So you would want to like verify the laws. I mean, like, there's a matrix of all the different combinations where you put LT, GT, EQ on one side and the same on the other, and then that's all possible multiplications, and then just verify that if you trace 3 levels anywhere, you get like the same thing, and that would be the associativity stuff. All right, now that we have this thing, now that we have a monoid, functions from anything in a monoids form a monoid, and so I'm going to create a whole new type. Call it comparator on A, which is going to be function M, the set of functions from A comma A into ordering. Now these are the things that like you would want to give to a sort function, because it takes a left-hand side or right-hand side and it tells you, are they less than, are they greater than, or are they equal? Okay, and so we've already gotten for free that comparator is a monoid. We don't have to like make it conform or anything. So there's a easy way to cook up comparator values from existing Swift ideas by extending comparable, and from the idea of a comparable, any conformance to comparable, you can cook up a comparator very easily so we need a closure with the left-hand side and a right-hand side. So if the left-hand side is less than the right-hand side, we'll use the LT. If the left-hand side is greater than the right-hand side, we'll use the GT, and otherwise we'll use the equal. All right, Swift is happy. So now we can cook up all types of comparators. We don't even have to define them like we did for predicates. We can just pop them out of nowhere just by doing int.comparator and string.comparator. All right, but we haven't really bought us anything new yet. I'll quickly just paste in allowing Swift standard library to understand what comparators are by making a sorted by, where you give it a comparator instead of a closure that takes a left-hand side, right-hand side. So now at least arrays understand. Like I could have, like, cook up some array sorted by int.comparator. Yeah. All right. This doesn't look any better than like anything we could have done with just plain vanilla Swift. So we got to try a little bit harder to prove that this is something interesting. There's a very interesting operator on ordering. All right, and it's called reversed. Okay, so given an ordering, it will generate a new ordering, kind of flipping the ideas of less than and greater than. So if self is less than, it'll switch it to a greater than. If self is a less than, it'll switch it to, if it's a greater than, it'll switch it to a less than, and then it'll leave equality fixed. And here's an interesting thing. Reverse is a function from ordering to ordering. Much like Brandon was talking about with laws and things like that, this also should satisfy some laws that if you have a function from a monoid to a monoid, you want it to play nicely with the structures on either side. You don't want just any function, because that you would just be collapsing information. And this is precisely such a morphism of monoids that preserves that structure, because if you took two ordering values and applied the reversed, you would get over to ordering. That should be the same as reversing each of them and then combining them. It has to play nicely with the combination on both sides. And reversed is such a morphism that plays nicely. So, given that, we can use that thing to also extend comparator. Now here's where it gets a little tricky. I cannot extend comparator because you can't extend generic type aliases in the way you would maybe want. It's not done yet. So I'm gonna extend function M where M is ordering, and then it's essentially the same thing. And so I'm just gonna go with it like that. But I can define reversed on it by taking a comparator and reversing the entire comparator. And so I can return function M where I just map into the monoid and then I reverse over there. And now I've got like a very nice way of just reversing the idea of a comparator. I can take that int comparator And I can just reverse it for free. Like I'm using like very small atomic units and like cramming them together in very interesting ways. All right, so in order to show the next benefit of being able to take lots of very small atomic units and like construct new things that's like kind of hard to imagine when you're trying to make something like much larger, I need to use lenses. Now, I've talked about lenses before. I'm not going to give the full definition of lenses. I'm just going to let it be known that in my sources directory, I've got some definition of lenses. They're just like just a wrapper around getters and setters where the setter returns a whole new value rather than mutating anything. And I've got a couple of models in my sources directory, and they've got a bunch of lenses I just have access to, and so I'm just going to use them. Like I have a project model, and inside there's like a lens namespace, and then I've got some lenses. Like I could lens into the creator. Then inside, composed with that creator, I could then go into the creator's location. And then inside the location, I could further go into the location's name. And yeah, now I've like this is a composed lens going from project to creator to location to name. And it would be kind of interesting to leverage that idea of lens, which has no concept of comparators, and derive comparators from it, like essentially for free. Like these two worlds don't have to know anything about it, but as me, the glue between the two worlds, I get to like piece them together in nice ways. And so I will extend lens where the part, the thing you're lensing into, is comparable. And now from here, I get to derive a comparator. So it's going to be a func called comparator. And it will generate a lens, or rather a comparator, on the whole. Kind of like I was talking about earlier, when you have functions into a structure, you a lot of times get to induce structure up on the set of all such functions. In the case of lenses, a lot of times, if you have structure on the part, you can induce that structure on the whole. And so by having the idea of comparable on the part, I'm going to derive a comparator on the whole. And you can do it in the obvious way. You got to return a comparator on wholes. I have a left side and a right side. I'm just going to use the lenses to like focus in. So I'll use the left-hand side lens to focus in, or sorry, I'm going to use the lens to focus in on the left side. I'm going to use the lens to focus in on the right side. And now I'm in the comparable world. I can do my less than and make that LT. I can lens in and do my greater than for GT, and then finally just equal. And maybe sorry. Thanks. All right, now Swift looks happy. So now this glue is going to pop out all types of structure that was kind of hard to see. I can take the project, and I can take any lens sitting inside it, like the creator, and I can look at anything inside it, like the location, and anything inside it, and the name, and I can derive a comparator from it. This is now a way of comparing projects by zooming all the way into the creator's location's name and using that to compare them. I happen to have a large array of projects sitting over in the sources directory. Oh wait, maybe it's something, might be called something else. Maybe all projects? Nope. Oh, projects, okay. So I'm going to quickly map that to a string so that we can kind of visualize. I'll just paste it. I'm going to drop. I'm going to drop this thing down and then bring it out. Oh, I hit the wrong one. Sorry. Not you. You. Nope. All right, there we go. All right. So here I have a bunch of projects. kind of in a whatever order. All right, I have 10 projects in various orders. It's got a state, live, successful, failed. It's got a location name and then like the project name. And I just want to start like doing things with it. Like for example, I want to sort them. So I could do sorted by, and I could use the project lens.state comparator to group all of the live ones together and then all the successful ones together. And bam, like I got that. Then I could further compose that with a project lens creator location name comparator. And now within each of the live and successful buckets, I've like now ordered them by location. So now the Brooklyn and then Los Angeles and San Francisco and so on. And like I can just keep on composing. So I might as well now compose this with the project lens name comparator for like one final sort that should be like have everything in a nice, well-defined order. And so now that puts 1 second every day up at the top of the Brooklyn live projects. But then like I can just keep on not only composing, but deriving other kinds of comparators. I could just like take one and reverse it. And now I've put Brooklyn at the bottom, San Francisco up at the top, but I've kept live the same and I've kept the sorting of the names the same. And then I could just pull out all of this, stored an array of sorts. Get rid of these little fellows. And then use our concat. I can just concat all of them together. And I just get one big old sort that does all that work. And this is kind of like you could imagine like an actual user interface with like being able to drag out sorts and reverse them and add more and remove some and everything like that. And this is like capturing all of that. And we just got like all of it essentially for free by having lots of small atomic units, gluing them together in like interesting ways. And it just keeps on going. You can kind of just keep doing this jazz. And that is the end of the talk, actually. So I'll just jump down here. I don't have a good outro. And I guess like one last thing would be like, yeah, we actually do this in our code base. It's not so like abstract that's not useful. Like it's very, very useful. Yeah. Okay. Yeah.
Other branding.
Yeah.
Define the diamond operator. Not random.
It's not a Brandon thing, but it's more of a Haskell thing than a math thing. Yeah. I never saw that in math. Any other questions? Well, I mean, it depends on what you mean by break. I mean, you wouldn't be allowed to sort by something that doesn't make sense, like sorting a project by a field that doesn't have because of the type safety. You could break, you think maybe you're sorting by one thing, but you're actually sorting by something else because you composed them in the wrong order. This is also an example of a non-commutative monoid in which, like, sorting by one thing and the other is not the same as doing the other. But yeah, it's about, yeah, maybe that clarifies. Yeah, you should just like, define the order. Yeah.
I noticed.
Yeah. I just need to put a precedence so that I didn't have to worry about parentheses, but, so I needed something. Monoid, you maybe want it to be a lower precedence because there's ways of layering on more structure. Like, for example, there would be something called a ring in which not only do you have this diamond operator, but you have a new operator, and they should distribute across each other in nice ways. And that means that operator maybe needs a higher precedence, or it needs a higher precedence and and things like that. Yeah.
There were a couple times where you kind of ran to the edge of the generics feature.
Yeah.
Since you also use Kotlin, are there Kotlin you can use?
Yeah, if I remember correctly, we haven't done this in Kotlin yet, but I believe it is possible to extend like the idea of a function in Kotlin so that you just get these things on function. Like I don't need to cook up a function wrapper that has a call field in it. I think you can just like extend function as an idea. And so that would allow you to do some things. But then also Kotlin has other things. Like I do not think you can extend a type to then make it conform. So then we've lost almost everything. But then it also has the idea of adding functions at least, or new capabilities to the idea of function. So yeah, it's good in some ways and then broken in other ways. I mean, I don't know why we do what we do. Everything's broken. But, I guess with this room, it'd be kind of messed up to say higher kind of types, right? No. I mean, yeah, of course, higher kind of types. You know, so Chris has a very interesting way of looking at monoids in which it kind of flips it, it bundles up all the operators into a struct, it basically type erases everything. And then from that, you can actually do that idea of a function from A into M, gives you a monoid all for free. You don't need to define a separate object to encapsulate it. So, you know, I probably don't even know enough about generics to know how I could bridge those worlds because I want to use this is how I would do math. Like I did math for far longer than I've done, well, I did it for a long time. And so this is how I think about mathematically. And I think I'm able to pop up interesting structures out of it. And then when I look at Chris's code, which somehow is more powerful, yet obscures other things. Like you don't get rid of the parentheses because you have to call the like op function always, and you're always getting those parentheses, and it kind of like, it doesn't allow you to see that structure. Yeah, so sorry, I don't even know if I know enough about generics too, other than just higher kind of types. Yeah. Okay. All right. Oh, one, yeah. I mean, I got to take a question from a Brandon, yeah.
Yeah, that was awesome. I think I covered, complimented, like you had it fresh stuff.
Yeah. It wasn't entirely idempotent. Yeah.
Awesome. That's so cool.
Yeah.
My question is, could you, if one were to convince others of power of lenses, this is an awesome example. But like on top of, so I'm going to use this.
Yeah.
But like on top of Swift structs that are already copy on write,
yeah.
It's hard to sort of do that. So what is your way to?
Right. Yeah, to me, a lens has very little to do with the get and set. It's by lifting it into a proper type, you're able to exploit structures that you do not get to see from the dot get set world. Like you don't get that composability. Like this is an example of one. And of course, if this popped up so kind of surprisingly, how many other, I mean, that's maybe like a very bad argument to make, but that is what happens in mathematics. Like if you embrace simple axioms and simple constructions, they combine in very surprising ways. And I think that's like helped mathematicians for a very long time, and it'd be weird of us to say that like that's not gonna happen for us. So to me, it's all about composability. It is not about get set and things like that. Composability, 100%, yeah. All right, yeah.